Hello guys, this is Sumant here. Today we'll be covering Chapter 8, Location Strategies from 12th edition of Heizer, Render and Munson. In this chapter, the authors talk about why choosing a location is a strategic importance. Strategic decision being for the reason that once a location has been chosen, it is not usually possible for the businesses to change it in short to medium term of time horizon. Yeah. So in this chapter, we'll deal with three types of methods to determine the best location. First one is the factor rating, wherein something that we've already done this in the previous couple of chapters. We're using some product for the weights. Then we'll also use the break-even cost example as to beyond, within a certain range, one location is better, and beyond a certain volume, the next location is better. And then the last one would be the gravity method or center of gravity method, wherein we choose the location based off of their importance. This is similar to the sum product or the weighted average, except that this time we are dealing with the coordinates or the geographical location. And the last one, which is beyond the scope of the course, but the introduction to the GIS systems, something that as an operations manager you should know. This is very commonly utilized as a specialized software that allows us to do various type of analysis using let's say census information or let's say fire locations or restaurants and so on in the marketing. This is also useful in determining, for example, if you want to target a certain section of the society. For example, if you want to open a pizza shop, then if you're targeting a particular age group of the population, then using the census data, you can say that where do most of the people of certain gender or both the genders live in an area of, let's say, 10 miles around the location, such that the age of the population within the 10 miles is between 15 and 35 and so on. Okay, let's get started with our chapter. First problem we are going to do is the problem 8.5, wherein we are given a location for a subway where they're trying to decide between the three options of Maitland, Baptist Church, and Northside Mall. The weights are given to us for different categories: space, cost, traffic density, neighborhood income, and zoning laws. And based on the importance of all these characteristics, they have a score for each location for the respective categories. Now, our job is to find out which location is the best given the importance of the categories and the score of each individual location. Okay, let's see how this can be easily done. So let us see how we can solve this problem, wherein we are given three different location choices. Let me copy and paste it here. Okay, so now we have three different locations for opening a new Subway restaurant. And let me bring this to wrap text. Okay, so namely Mainland, Baptist Church, and Northside Mall. Those are the three locations that we have. Now we are also given the categories and the respective weights for each of those categories. So first thing we want to find out is what is the collective score. Let's say for the Mainland, if the score of 60, 40, 50 and so on, but these are weighted differently. So first we want to find out the collective score, which would be 0.3 times 60, 0.25 times 40, 0.2 times 50, 0.15 times 50, and 0.1 times 80. The summation of all of those resulting numbers, we want to calculate that here. So then we have one collective score for Mainland. We want to do the similar process for the Baptist Church, where we will be multiplying 0.3 times 70 plus 0.25 times 80 and so on. Okay, so before I get any further with the calculations, I want to check if the sum of all the weights is equals to 1. This would this acts as a check in avoiding any mistakes. So let's say equals to sum product. I'm going to select the weights, hit F4 to freeze, and then select the mainland scores, mainland scores. Now, if my formula is right, then I should be able to drag in and for all the locations. And if I hit F2, I can see that my weights are still selected correctly times the north side mole. The summation of the products between 0.3 times 80, 0.25 times 30, 0.2 times 60 is given in this cell. Okay. So given this, since this is the score, right? 3 locations are being considered. Following tables are factors for each side. So in this case, the more the score, the better it is. Yeah. So in this case, Baptist Church seems to be the best location so far. Now it also says if the weights for space and traffic density were to be reversed. Okay. So if this is the case, I'm going to copy and paste it again. Now it says the score if the weights for space and traffic density are reversed. Okay. So the space and traffic density were to be reversed. So if this was to be 0.2 and this was to become 0.3. Now before I want to drag, so then it's referring to the correct formula, wherein if I was to make a change, it should reflect in the calculation. So 0.2 and this becomes 0.3. By doing so, the location with Baptist Church still stays the best one. Okay, so that's our conclusion. Given the factors, given these factors and given these weights, given all of these scores for these 3 different locations, we should choose Baptist Church. Okay. The next similar question we have is there's an insurance company that's considering opening an office in 2 different locations, Philadelphia and New York. So we want to make sure that given the information, we can make a decision about what type of, which location should they be opening their office at. Okay, so now we are given the various factors: customer service, banking, accessibility, computer support, rental, and labor cost and taxes. We are given the weights for each of those factors. Yeah. Now we have choice of location 1, Philadelphia, the second one being New York. So first thing we want to do is, given these weights, we want to come up with a combined score for all of these scores across different categories, such that we have one score for Philadelphia and we have one score for New York, such that we can say which one is a better one, such that this is 0.25 times 70, 0.2 times 40, and so on. And then whatever the resulting numbers of these products are, we want to keep adding it up, such that we can say if let's say the score for Philadelphia or New York is better. Okay. Now we'll use the same formula as we have used before. Sum product and hit F4, and we use all the scores for Philadelphia and for the New York. And I'm also going to use sum of all the weights just to make sure if they are 1. Had they not been equals to 1, then instead of using 73 as such, the resulting number we would have used is 73 divided by the sum of weights. Now anything divided by 1 stays the same, therefore we need not do it. Okay. Now given these total score, weighted score for Philadelphia and New York, Philadelphia is a better choice. Yeah. Now the next type of question we have is for the fixed and variable cost. Now we are given the fixed and variable cost for 3 different sites. Yeah, so let me get this over here. So we know the fixed and variable cost for 3 different sites. site 1, site 1, site 2, site 3. They have a fixed cost annual 500,000, 1700. Variable cost is also given to us. Now the deciding factor would be for what range of production is site 1 good, for what range of production site 2 is good, and 3, and so on. Now this is based off similar concept of break-even analysis to what how much do you have to produce in order to recuperate your investment cost. Okay, so using the same concept, we are going to solve this first by hand, I mean in Excel, but by comparing the way we would do if we were to solve it by hand. Yeah. So first I'm going to show you how our calculations are supposed to be done. So let's say if this is what we had, okay, this is the problem we are dealing with currently. Control Shift and okay. Now first thing is we want to make an equation. Let's say between site 1 and 2. Let's say the site 1 and 2 are equivalent in terms of importance at volume x1, okay, which means 500,000 plus 11 times x1 should be equals to 1000 plus 7 x1, okay, which means that we can rearrange this 11x1 minus 7x1 equals to 1000 minus 500. So x1 is equals to 1000 minus 500 divided by 11 minus 7. This comes out to be the break-even point between site 1 and site 2. At this point, a rational business manager is equally likely to choose site 1 and site 2. So this will come out to be 500 divided by 4, which happens to be 125. Yeah. So similarly, we are also going to calculate the equivalency point between site 2 and site 3. Site 2 and site 3. So that would give us an equation of 1000 plus 7x2 equals to 1700 plus 4x2. Okay. At this point, x2 would come out to be, going by the same process as before, 1700 minus 1000 divided by 7 minus 4. Yeah. Now this is the calculation we can also put in Excel. So this will become 700 divided by 3 equals to 3 2s are 6, 3 3s are 9, 3 3s are 9.33, and so on. Okay. Now, therefore, anything less than 125, site 1 would be good. Anything more than 125, site 2 would be good. Okay. In this case, for site 2, anything less than 233, site 2 is better. Anything more than 233, site 3 is better. Okay. Now, it's always good to check, but combining the results so far, we have anything less than 125, site 1 is better, and the range goes on till 233, after which site 3 is better. So the range of 125 to 233, site 2 is better. Anything less than 125, site 1 is good. Anything above 233, site 3 is good. Now let's do this in spreadsheet and also try to make a graph that'll help us visualize this process. Okay, so then our understanding is more clear. So first I'll try to compare site 1 and site 2. Now we already made the equation for this and we came up with a calculation of this one here. So we're going to do the same thing in spreadsheet. What did I do? Okay. There. Okay. So first thing we want to calculate is let x1 be the case wherein site 1 and 2 are optimal. So let's say if at x1 both of these are optimal, then that x1 is going to be equals to 1000 minus 500 divided by 11, parenthesis, 11 minus 7. Okay, so that is comes out to be 125. And then I'm going to compare site 2 and 3. Let that be x2. With a similar process, it'll come out to be 1700 minus 1000, right? Divided by, start of parenthesis, 7 minus 4. Now, this is site 1 and 2. This is site 2 and 3. Okay, now it's not required in this case, but there may be a scenario wherein you also have to compare site 1 and 3. Let's say if that was to be the case, let that be x3, site 1 and 3. Now all you have to do is put in the values for site 1 here, and that should reflect you the boundary between site 1 and 3. Now this would be the case if site 2 did not exist. Then site 1 is good as long as the volume is 171, and beyond that site 3 would have been good. Okay, now because site 2 is there, site 2 works better between 125 and 233. Okay, now if you want to visualize this, let's see how we can do that. Now let's write down the equation for every site. So let's say for site 1, our equation would be $500 investment cost. Let me write it like this: 500 plus x times the variable cost, which is 11, or $11 times x. Now this x is not known to us. Yeah, let's say if x was to be 0, then volume was to be 0, then the cost comes out to be, so at x equals to 0, our cost turns out to be 500 plus volume times 11. Yeah, now using this I can calculate the cost for, did I use it right? How come this is 1000 yet? Oops. Okay, let me bring this here. Okay, I was supposed to use this for site 1. Okay, now if our volume is 0 it stays 500. If my volume is 1000, then it should give me the exact point. Okay. Now in this case our range is around 233 or something, so let me calculate this for 300. Okay. Now I can also calculate this for site 2. Our equation would be 1000 plus 7 times x. Okay. Now let me copy the same thing here and then edit it such that this time it should refer to site 2. Okay, good. Now let me copy this here as well such that it should refer to the equation for numbers for site 2. However, this time we are going to calculate again for 300. Okay. Similarly for site 3, our equation would be $1,700 plus 4x. So this case it would be 500. Okay, I need to change this. Okay, such that drag and drop 300. Okay. Now that we have 2 points for each of the equations, yeah, for each of the sites, for this equation we have the condition when, okay, come on here. Okay, for site 1 we have 2 points. This is point 1, 0, 500. That is part of this equation, and also 300, 3800. So if you were to plot these 2 points, they should fall on the line that is represented by the equation 500 plus 11x. So on any graph we will have a line wherein one of the point is 0, 500, sorry, like this, like 0 if this was to be the volume and this was to be the cost. So at this point volume is 0, the cost is still 500. Yeah. And the next point would be when volume is, let's say, 300, the cost would be 3800. So we will have a line. Similarly, we will do this for site 2 and site 3. Yeah, so let's say what that graph looks like. So I'm going to select insert and use a connected point such that I tell it that the series name is, come on, oh no, I can't select it here. Okay, then do the same process again, select data. I don't need this, I only need one. Edit such that the series name is this, represented by the equation. X's are 0 and 300 and the Y's are 500 and 3800. Okay, so this is represented by the site 1. Now we want to add the next series where in site 2 the X's are represented by 0, 300 and the Y's are represented by 1000 and 3100. Hit OK and add one more. Site 3, X's are 0, 300 and Y's are 1700 and 2900. Okay, so now this makes it more graphical, which is a lot easier to understand, as now you can see that this site 1 is represented by the blue line. So site 1 is the lowest cost because this is all the costs, this is all the volumes. Okay, 0 to 350. This is the scale. That's how we chose the 300, being this 233 as a hint. So I wanted a little bigger number. So site 1 happens to be the lowest cost, yeah, as the volume increases from 0 to 125. Yeah, so at this point, site 1, till this point, site 1 is the lowest one. After this 125, site number 2, which is represented by orange, this is the lowest cost of the two. Okay, had this site 2 not been the case, then site 1 would still have been better. Okay, now since site 2 does exist, site 2 is the lowest one for the range of 125 and 233. Those exact numbers are here, 233. So this is good to know those exact volumes. This process is good to visualize the overall 30,000 feet bigger picture. And beyond 233, so let me write this down. This is at 233 volume, and this is 125 volume. Okay. Beyond 233, site 3 is better, which is represented by gray. Okay, so this is the full explanation of this type of question, wherein we have to make a choice as to which site is better given our volume. So if you know how much, in what range your production is going to be, then accordingly you can decide now as to which site is better. If you already know your volume of production is going to be 250 or above, then you should always choose site 3. If you know your volume is going to be between 125 and 233, then you choose site B. If your volume is going to be less than 125 in future, then we choose site 1. Okay. Now, using the same process, I'm going to show you how easy it becomes. Now, this is especially for those of you who try to solve this on calculator or on pen and paper. It's easier to do certain things on pen and paper, but let's say if you were to solve a different question for this insurance company that is using annual fixed cost and variable cost per auto produced. Now this is a totally different question, right? Now if you have correctly solved the previous question like I did here, then all you have to do is copy and paste, and you have all of your answers reflected. Okay, hold on. So let's say this is what I had here. Then all I need to do is this, and this one was 2 and 3, so equals to 2 and 3, and this is for 1, and this is for 3. Okay, now given this, our numbers are such that between x1 and x2, the break-even volume is 20,000. Between x2 and x3, 5,000 is better, and between x1 and x3, 10,000 is the point, which means below this amount. Let me do it, Control Shift exclamation. So below 10,000, x1 is better. Now you comparing 2 and 3, x2 below 5,000, site 2 is better. Anything less than 20,000, site 1 is better. Therefore, our resulting conclusion would be, so let's see if we can visualize this to make our lives a little easier. You're talking now in the range of somewhere between 5,000, 10,000, 20,000. So if you were to plot a graph between 0 and 30,000 or 40,000, that should be sufficient. So 0, 0 is fine for all of these. I'm going to make this, let's say 35,000, 35,000, and bring the same thing here, 35,000. Now this makes our life a lot easier. How so? Site 1 is always better. Now in this case, was called, instead of site 1, it was called site A. Yeah. So site A is better up until the volume of 10,000. Okay. After that, site 3 is better, which would have been site C. Yeah. The second one, the orange one, is never the lowest cost solution. Now, this gives us the benefit of being more accurate despite having done the mathematical calculation here. Okay, so this mathematical calculation has its own advantage, and plotting them graphically has its own advantage. Graphical solution gives you the 30,000 overview, bigger picture view, and once you have that bigger picture, then this helps you understand being more accurate. So I would always suggest that you do this type of calculation to find the break-even point between two sites at a time by comparing them one with the other, and use the graphical solution to get the bigger summary type of picture, because this makes it very clear. If you try to stick with only mathematical side, wherein this one tells that anything less than this, site 1 is better, anything beyond this, site 2 is better, anything less than 5,000, 2 is better, anything greater than 5,000, 3 is better, anything less than 3, 1 is better, 3 is better, right? So all of these combined does not give you immediate clear picture, but if you were to plot them using the individual equations for each of the sites, then it is clear that at 10,000, site 1 is better, and beyond this, site 3 is better, because this is represented by site 3 equation. Site 2 is never better. Okay, so this is this helps us, the combination of mathematical side, and the graphical is the best way to go. Now remember, this is only that I try to solve using one pattern or one methodology for this question and for the next question. Okay, even though the numbers are different, now the only luck I had was that they were both done using 3 sites comparison. Okay, if there was one more site, then we would have repeated the process for one more combination or 2 more combination, however the case would have been. Okay, now the next type of problem we have is the coordinates for various locations are given. For city A through G, we are given the coordinates of x, coordinates y in the same format, x comma y. So we have 5 and 8 as the given location for city A, and let's say 2 comma 6 for the city G. Now we want to find out which of the city or any other point would be the best place to serve all of these for being a central hub. Now we are also given the shipping loads that are going from either of these locations here. So for city A, we have a shipping load of 5. For let's say city C, which is located at x coordinate of 4 and y coordinate of 9, has a shipping volume of 15. So we want to find out what would be the best place to locate our central hub, such that it takes care of all the locations that it can serve, which is given A through G. Okay, now first things, let me copy this and paste them here. Now if you look at this, first thing we want to do is calculate a weighted average for all the cities, which would be A through G. Okay, or let me do it like this. However, unlike last time, this time if we were to use our shipping volume as weights, the summation of weight is not going to be equals to 1. Okay, so therefore we do need to divide our end result by the sum of the weights. So weighted GHTD weighted x would be this times this divided by 65. Okay, now either we do this, or we can also go by the fact, let's say, okay, hold on, let's do this way, equals to this times this, such that I freeze the column but not the row. Okay, and paste this. This would be, let me correct this one, coordinate times shipping. Okay, now this is for x and this is for y, such that this one, oops, well, I froze the wrong cell. Okay, so let me come back here and correct this. So I want to put a $ for the column n in this case. Okay, so that when I paste it here, okay, so this, what it does is, we are doing 10 times 5 is represented in this cell, and 5 times 5 is represented in this cell. Okay, now we are going to copy all the way down. Okay, Control C and all the way this. Now when you do the sum of all of these individual, now this is for the x coordinate, this needs to be divided by 65. I'm going to freeze this so that I can copy this for the next cell. And now we have the coordinates x and y, that we can say that these should be the coordinates for, where should I write this, central hub. Okay, now the central hub should be located at this point. Therefore, an easier way to do this, to graph and so we can get a better picture, is I can select these and say insert an XY plot. This seems to be something weird. Okay, select data. I don't know this. Edit. Let's say city. All the x coordinates are in here. All the y coordinates are in here. Okay. Hit OK. And I'm going to say show me the callouts. Okay. So now we have all the points visible to us, such that 510, the first point, is located here. Now at this point I can say select data, hit add, series name central hub, x value is 5.15 and y is 7.3, hit OK. Now this shows immediately where our central hub should be located. Now if a central hub was to be located at this location, under hold on, this Control Shift A, nope, Control Shift $, nope, Control Shift, nope, come on, okay, better. Excuse me. So if the central hub was to be located at 5.15 and 7.31, and whatever the leftover value is behind the decimal, we don't care for this case, then it, as long as these shipping volume stays the same, then this is the best location. If any of the shipping volumes were to be changed, let's say instead of 5 at city A, it becomes 50. Now, keep attention here at this point. If we were to change from 5 to 50 here, this point should move closer to the A. Or if this location is F, if this was to go, then we'll try that too. Okay, change for location F. Let's see, how does that affect? So if this was to be 50, the point moved, correct? If I was to make it to the original point, this point comes back. Now, for let's say for volume F, all of a sudden, if this volume was to go high, so currently this is at volume 10, therefore, and F is located where? 3, 2. So this is F. Yeah. So if our volume of 10 was to go up, then let's see how does our central hub's location changes. It was to go from 10 to 100. Then you see how the location for the central hub immediately got closer to F, because now it has more weight, yeah, compared to everybody else. It is shipping more volume, therefore it has more importance, and given the way we are calculating our weights, it has higher importance. So this would be the importance of F would be 100 divided by sum of all of these, which would be 155, yeah, in this case. So the percentage importance of F increased quite a bit. Now, this is not asking the question, but I'm just giving an example, and also the benefit of doing these live calculations, so then if one thing changes, you don't have to redo the whole problem. Okay. So let us answer the question that is asked by the textbook. Near which map coordinates should the hub be located, and if the shipments of city A triple, does this change the coordinates? Okay. So first thing is, given this location, given the shipment volume and location, our hub should be located to 6,8. 6,8 is city B. So that is the closest we can see on the graph. Also, if this was to triple, if it was to go from 5 to 15, then our new location for the central hub would be 513 and 767, which is again shown in this map. Now, okay. Now, one more thing I wanted to show was, let's say currently this graph only shows you the location of the cities A, B, C, D, and through G, and this orange one shows you the size, the location of the central hub. What if we also wanted to communicate the importance of all of these locations by their shipment size? Now, the way you can do this is, let me keep this graph as is and paste this at separate place, and now I can make the changes to my original one, so then I always have a working graph. First thing I want to do is right click on this and save, change chart type, and do a bubble size. Now currently all of those points are represented by the bubble. I also want to then click format, right click format series, and plot series on secondary axis such that this shows up. Then I right click here and say format axis, select data, city, edit, and choose the bubble size. Yeah. Now bubble size, let's say I want them to be represented by the shipping loads. When I hit that, hit OK, now all of those locations are represented by the relative shipping volume that they are, each of the city is handling. So it shows us the importance of each of the location by the size. Now we can do the same for what was it, our central hub, such that central hub can also be shown, let's say, by bubble size of let's say at this point I just want to make it visible, so let's say it'll be handling all of this volume. Let's make this one, it might be a little too big, but okay, So that's where the central hub would be. If we were to assume that all of this shipping load is going through the central hub, then that gives the location of the central hub and its size in relation to the location of all the other cities and all the shippings that is being handled. Okay, so this is how you can depict more information on a single graph. Okay,